welcome to the another session of this 5 days faculty development program titled GIS and Remote Sensing, organized by Department of Civil Engineering, Government Engineering College Bilaspur and sponsored by AICTE under the AICTE Training and Learning Scheme. The topic for this very first session is Introduction to GPS Receiver and brief about IRNSS presented by Dr. Ashutosh Bhardwaj, scientist at Photogrammetry and Remote Sensing Department, Indian Institute of Remote Sensing, Dehradun. He has completed his bachelor's degree in civil engineering from NIT Raipur and master's in remote sensing from BIT Mesra. Later on, he earned his PhD from IIT Roorkee. He joined ISRO in the year 2001 after a brief career as a faculty at the Department of Civil Engineering, BITS Pilani. From last 20 years, he has been engaging in industry, teaching and research in surveying, photogrammetry, GNSS, cartography, remote sensing and topographic modeling. He has published over 50 research papers in different journals and conferences. He has widely contributed to various projects related to remote sensing at NRSC and IIRS. He has received appreciation from the Ministry of Planning and National Development Republic of Maldives for rendering expert services for GPS ground control survey in the National Mapping Project Maldives. Sir, we are honored to have you here for this session.
Thank you, madam. It was a good detail about me, so I thank you for you. Okay. And I welcome all the course participants who are there in this program where we are having the faculty development program under the AICTE. So I will be starting this topic and it will have some basics to some advanced things. So now I will start the lecture part. So basically it will be on the introduction to the global navigation satellite systems, which will cover the GPS, Galileo, Beidou, GLONASS, all those systems, and including the Indian Regional Navigation Satellite System, which is our own system developed by India. So some historical part we will see. Basically, see when we are talking about the global positioning system, what we are doing is basically the surveying. So many of the technical areas such as the civil engineering, agriculture engineering, geography, geology, those people are highly attached to this surveying activity. And as we have seen during the initial phase of the development of human being, we have been using the mental maps, using the celestial navigation systems with the help of the sun, moon and stars. And then when we have gone through the various civilizations on ground, historical civilizations which are not there, we have seen that the remnants have a good layout of the colonies with perfect 90-degree roads, good ventilation schemes. So that means they were also involved into the surveying activities and provided good amenities to the residents of those times. So in civil engineering and other subjects, we start our instrumentation part, starting from the chain, tape, going to the theodolite, tachymeter, compass, various levels, electronic distance measurement devices, and then the total station. So there we are covering into the civil engineering portion, and thereafter in some of the places as an optional part we are covering the GPS and the remote sensing also, including the photogrammetry. And all these methods use the classical method, that is the triangulation or the trilateration for the surveying. Now when we are coming to the satellite sciences, how this all has been integrated is that when the first satellite was launched, that is the Sputnik 1 by Russia, and then the Explorer by USA, then they have a issue of tracking the satellite into their orbit. So they use the Doppler shift method for that, and in the times to come thereafter, soon what they realize that it is helping them in calculating the geodetic discipline parameters also. So once the satellites were launched in 1957 by Russia and 1958 by US, in 1958 itself, the Earth flattening was computed using the satellite orbits. So that was one thing. And then thereafter, you might have seen that the GRACE, GOES, CHAMP, various gravity satellites were also launched, and they are giving us the gravity or the gravity anomaly. So that is the length and width of the topic. Basically, what we are covering, that which is a merger of the surveying technique with the latest satellite based techniques involved in basically the area of the surveying and to resolve the problems of Earth, what is the shape and how the gravity plays a very important role in it. Now, when we talk about all these instrumentations, starting from the chain to the total station, there was a clear-cut requirement to do the survey, and that was the line of sight requirement. So if we do not have a clear line of sight requirement between the equipment and the staff or the reflector, then it is difficult to do the survey. And this difficulty was not there in the case of the GPS or the GNSS. So we are directly getting the signals from the satellite, and thus this is the first technique which made this possible to do surveys across the country. So you can have a receiver in Jammu and Kashmir to Kanyakumari. Like in case of a National Remote Sensing Center, we have a ground control point network across India using the 26 stations. Now these stations are not visible from each other on the ground, but still they are part of the survey network. So that is the power which we have the access through the global positioning system or the GNSS. And therein we have added the Indian Regional Navigation Satellite System, which is the wholly owned setup by the Government of India through the ISRO. So again, some part of the history we will take about. So historically, we have seen that various technologies has been developed for the purpose of surveying and the navigation, from the times of the mental maps to the markings on the stone trees or the monuments, to the development of magnetic compass, gyro compass, radio direction finding, and then for the defense purposes, the radar also was developed during the world wars, and that also helped in such activities. And later on, in 1940s, we have LORAN-A, long-range navigation systems, which are tower-based, radio-based, low-frequency systems. They were developed by the US, and then it resulted into finally the LORAN-C system, which is still active. So it is again a high-frequency radio-based system, and this is the based on the tower-based system. The way we have our mobile services, so similar kind of towers are there. Of course, difference will be there. They are quite tall towers, and the maintenance will be very high. And a group of 8 LORAN-C towers has a capability to cover large part of the globe. So that is the kind of this LORAN-C system is there. At the same time, the Chayka, that is another parallel system developed by the Russia. So these were the ground-based tower-based systems. So these are the providing the terrestrial navigation for their Cold War era requirements of those times. And thereafter, the first global terrestrial system was developed, which is tower-based. That is the Omega system by the US and the Alpha by the Russia. Once these developments were taking place almost parallelly in case of the US and Russia, and thereafter the development of transit was done. Primarily to meet the requirements of the US Navy, and the Cyclone for the purpose of the Russia to meet similar requirements. And in 1980s, we saw the emergence of the GPS, the first satellite being launched in 1978, and then the initial operational capability for the GPS, that is the global positioning system developed by the USA. The initial operational capability was completed in 1993. Same happened in case of Russia. They are able to get the IOC for the GLONASS in 1993. And in 1995, both the countries, US and Russia, they are able to fully develop with the full operational capability their own satellite-based navigation system in 1995. Then the international GPS service also started in 1994, and now it has been renamed as International GNSS Service. So once the Cold War era has vanished, and the Russia and the US came together, and after 3 rounds of meeting in 2006, so they agreed to share the codes, and that gave rise to the development of the terminology which we use today, that is the Global Navigation Satellite System, which is a system of systems using the constellation of constellations. What does that mean is that in the single receiver we are able to receive the GPS signals as well as GLONASS. Before 2006 it was not so. If you want to have GPS service, we have to use a GPS receiver, and if we have a GLONASS service, we have to use a GLONASS receiver. But when the GNSS has been conceptualized, it became possible for the vendors to prepare hardware wherein in the single receiver we receive both the signals like the GPS or the GLONASS, similar to the dual SIM mobiles which we are using, where you can have Airtel or the BSNL signals together in the same mobile. So same thing happened in 2006 in case of the satellite-based navigation systems. So post this time, what has happened? The dismantlement of the tower-based system started, but later on, because of some international developments, it was realized by the governments that we cannot do away with the tower-based systems. We cannot depend upon the satellite technology only. So that started the redevelopment of the Lorentz systems. So enhanced Lorentz system came into picture, and it started providing an accuracy of the order of the 20 meters, and enhanced Chayaka system was developed by the Russia to meet their requirements. So now we have a time when we have the terrestrial navigation systems as well as the satellite-based navigation systems. So post scenario when the disintegration of Russia took place, there was a fall in the GLONASS services because of the shortage of the number of satellites required. However, they could meet it in 2010 again, and the GLONASS services also resumed thereafter. And the QZSS, quasi-zenith satellite system, also started its development by the Japanese government. Then in 2010, the conceptualization was done to have integrated receivers where we have the satellite-based receivers which have GNSS signals and the ground-based tower-based signals from the E-LOREN or the E-Chayaka. So these systems also came into being. So this is the kind of the chip what they are using, 6 centimeter only, and it has the accessibility to E-LOREN, E-Chayaka, and the GNSS system. So it is an integrated chip providing the satellite-based navigation system as well as the terrestrial-based navigation system. It is coming from the Relectronics. This is the company Relectronica, and thereafter you might have heard about differential GPS. So similar to that, there is an enhanced differential LOREN also. So the ground-based technology, the terrestrial-based navigation also developed parallelly to a high level of accuracy with time. Then in 2013 to 16 time frame, the Indian government, that is the Indian Space Research Organization, also developed the IRSS, which meets the requirement of the country, and it covers the area of India and 1500 kilometers beyond the Indian border. So it has also a large footprint, and it is a regional system. So it is not a global system. BIDO, which is developed by China, it has got completed in 2019 and with remaining 2 spare satellites to be launched in 2020, and they were also launched recently. So BIDO also completed its configuration. So right now there are 3 systems, GPS, GLONASS, and BIDO, which are global systems which are fully operational, and 2 regional systems, quasi-zenith satellite system by Japan and IRSS, that is Indian Regional Navigation Satellite System by India. So now we have a situation where we are talking about the merger of the satellite-based navigation system and the terrestrial-based navigation. So this is a pictorial view of where the terrestrial-based navigation systems, which has towers at various places with control stations and the user segment also. This displays the global LOREN coverage, the places of towers where it is there in the US, and then this shows the merger of the satellite-based navigation system with the tower-based navigation systems. And thereafter, around 2 years back, Xiaomi Mi 8 also came, which became the first smartphone which can provide dual frequency GNSS signals, and they can be processed at its end. What does that mean? That we'll discuss. And then now Navik is also available with the new Snapdragon Qualcomm chips. So Navik signals are also available in the mobiles. In Europe, there is a service called Eurofix. So that is again a merger of the terrestrial-based navigation systems and the satellite based navigation system. So I put some of the screenshots because there is a lot of detail in it. Then recently the IIT Bombay team also developed a chip for the IRNSS. So that chip is also available. Once it is put in our mobiles, so we will have more and more facilities, and the app development can be done. Then the development from the Android 7 onwards is that the IRNSS packages are involved into the APIs in the level 29. So that is another availability of IRNSS signal and its compatibility with the latest Android versions. So which open the way for the development of various applications. So that was the whole development thing which was happening, and now we will come back again to the basics, and then we'll gradually cover the various components of the global navigation satellite system. So as I briefed initially that with the launch of the Sputnik, using the Doppler shift, the satellites were tracked. Now at the same time, there was a scientist called Frank McClure at Applied Physics Laboratory. This was the person who gave the idea that whether it is possible to invert the problem. So what is the problem actually? The problem when we launched the Sputnik was that we have known points on the ground, but we have the unknown point, that is the location of the Sputnik in the space. So known is on the ground and unknown is in the space. So the inversion of the problem will mean known in the space and unknown on the ground. And using his team, Frank McClure was able to find that mathematically it is possible to do that. And that started the development of transit, which was for specifically for the US Navy, helping its ships and submarines. It is a set of 6 satellites covering the area of interest of the times at that moment, covering part of the globe, mainly the Pacific or the Atlantic region. Similarly, Russia also developed Cyclone system, which was having 10 satellites. However, the Cyclone has a military as well as the civilian component, both were there. Now, the limitation of this system was that they were able to provide the static user 2-dimensional accuracy only. So what happens that latitude, longitude only we will be able to resolve. Height we are not able to resolve when we are using the transit system. So, but to meet those days of requirement, X and Y were more important because they were talking about the ocean. So it can be roughly estimated as the mean sea level. So that is how they were meeting the requirement of the Z. And then the second limitation was that once you switch on the system, it takes about 40 minutes to give you the value, which is highly intolerable in today's environment, because in today's environment, when we switch on the system, immediately in few seconds, we are able to resolve the first fix. First fix means the solution of the equations used for calculation of the X, Y, Z. So if in few seconds we are getting it now. So in 1995, when the GPS and the GLONASS both achieved their full operational capability, so we can see here that for 1 year there was a overlap with the transit system. So transit system was abandoned after 31st December 1996, as it was redundant now. Now these computations of orbits, they helped the scientists to develop the Earth models, the standard Earth model by the Smithsonian Astrophysical Observatory and Goddard Earth model by the NASA Goddard Space Flight Center. So if we see GPS, we should not see it just as a position or navigation giving equipment. Actually, it involves a lot of science in it, including the precision nutrition of the earth, what effects are there of earthquake and tsunami, how they are changing the parameters of the earth. All those things are being actually studied and affected. And we are studying these with the help of the continuously operating reference stations, which are dispersed all over the globe. And a lot of things are happening into the geodesic component, and those things are primarily taken care by the International Earth Rotation Service. So IIRS is the agency which take care of all those parameters and finally give away us the value of the WGS 84 datum, which is not static, that is also dynamic. The name is static, they do not change it after 1984. Earlier we used to have a WGS 72, WGS 70, WGS 64 also, but now we have WGS 84 also, whose parameters basically the major and minor axis of the earth, those values are being changed with the help of the IIRS, because IIRS takes care of the International Terrestrial Reference Frame, which is the mother of all the reference frame, we can say, and those parameters are later on shifted to WGS84. So like this, we saw a lot of development in the global navigation satellite system and the geodesy in general, helping us to do the crustal deformation studies and bring the different datums together. So in 1970s, it became possible to do the datum transformation, but they were having an accuracy of the order plus minus 50 meter, which may seem to be poor in today's terms, but which was a very good accuracy in those days, because before that it was not possible to shift one datum from the other datum, because different datums are local best fit curves, whereas the today's datum which we are working like WGS84, they are the best fit curves to the entire earth, so they take care of the requirement for the entire globe, irrespective of the boundaries. So finally, satellite navigation systems are providing us the geospatial positioning in an autonomous mode. 4 systems have been under development, that is the Navista GPS, GLONASS, BEDO and Galileo. All of these except the Galileo has completed the configuration. So these 3 are fully operational, Navista GPS, GLONASS and BEDO, whereas Galileo will also be soon completing, as Russia is helping the European Union now in various launches of Galileo satellites. So we will see soon the completion of Galileo also. Among the regional systems, so basically what we can say is that the transit and the cyclone, which were developed during the Cold War time, they were the first regional systems. However, they are not there now. So in today's terms, the regional systems which are operational are the IRSS, that is the Indian Regional Navigation Satellite System by India, and the Quasi-Zenith Satellite System by Japan. And you might have already got the news that last week the IRSS signals has also been approved for the navigation services in the ocean. So that is the latest development. After the certification of IRSS signals with regard to its format, now it is fully operational in the Indian Ocean region and in the Indian region. So various agencies have certified and full use of IRSS can be done in its footprint area. So this is the family of GPS satellites which you will see in detail, and these are 2 views. One is the top view, so instead of 6 orbits we see the 3 orbits. So basically the Navista GPS is using 6 orbits at an inclination of 55 degree to the equator. Each orbit is having minimum 4 satellites. So initially the satellite based navigation systems were meant for the defense only. However, because of some of the tragedies and President Ronald Reagan, at that time he declared that it will be used for the civilian purposes also. So when this Korean flight was shot down, it was a massive loss of 269 lives, and which changed the mind of the world to use the GPS for not only the military applications but for the civilian applications too. And now we see that there are endless number of applications which has been developed and which are dependent on the signals of the GNSS in today's scenario. So primarily what we are getting from Navista GPS is the position, which means the latitude, longitude and the height, and then we are getting the velocity of the receiver and then the time also, because the GNSS systems are using the atomic clocks, which are actually ensembled clocks. There are hundreds of clocks, 200 plus clocks are there, atomic clocks, which are giving after the modeling a single time. So the GNSS timing is actually working as a timing laboratory also, with which we can reference the other things. Then the space-based signals are having upper hand as compared to the ground-based signals, because the ground-based signals have the attenuation or the line of sight problem. So if you have more trees or built up regions, high-rise buildings, so we can see the problems in the signals of the ground-based equipments. Now in this whole work, the International Civil Aviation Organization also plays a very important role, because they have to make the standard operating procedures for the flying of the aircrafts across the globe safely. So from their perspective, they have given the definition of GNSS as a worldwide position and time determination system that includes one or more satellite constellation. What do we mean by one or more? One means either the GPS, either the GLONASS. Whereas when we talk about one or more, so that means we can have GPS, GLONASS, BEDO, Galileo, IRSS, QZSS. All these signals can be used together. Then there are receivers on the aircrafts also, and then there are system integrity monitoring systems working on the ground, which are basically computing the errors at known locations. So all these things in an integrated fashion are providing us the necessary accuracies to support required navigation performance for the intended operations. So that is how the ICAO looks at the GNSS, and we also do look at this in the similar fashion, because we are also working in the multidisciplinary areas and we need to touch various applications which have various requirements. Similarly, the satellite-based augmentation systems were also developed. So here also Gagan is there, which is developed by India. However, the Gagan is a dependent system. It need to have the GPS signals as a feed and the correction parameters from some of the known locations. So we are dealing with a multi-model system now. However, the GNSS is providing us a large number of satellites now with a much more strong mathematical component for calculation of various corrections as well as the final positioning. So this is the some of the general characteristics for the GPS, GLONASS, Galileo, BEDO, and these are summarized in the form of this table, where we can see that the positioning accuracy is of the order of 10 to 20 meter, which is provided by either of these systems. Velocity they are providing is order of 10 centimeter per second in case of Navistar, GLONASS, to 20 centimeter per second for Galileo and BEDO1. BEDO1 is the regional system of the BEDO, because in case of China, they have done a very smart design. They have scaled up the regional system into the global system, whereas the global system, which is the BEDO2, they are able to provide velocity of the order of 40 centimeter per second globally. Similarly, timing accuracy is of the order of 1 microsecond. In case of Navistar GPS, in today's scenario, it is about 15 nanosecond. And for GLONASS and Galileo, it is 20 nanosecond. For BEDO1, 20 nanosecond, whereas for the BEDO2, which is again the global part, has about 15 nanosecond accuracy. So all these 4 satellite-based navigation systems are using different ellipsoids, that is the WGS84 parametric assembly and the Galileo terrestrial reference frame and the China geodetic coordinate system. However, the transformation parameters are known. So as a part of GNSS, these can be resolved mathematically. So the GPS has 6 orbits in which minimum 4 satellites are there. So which makes it 24 satellites. However, the dependency on the GPS applications has increased. So a lot of care is taken and a lot of redundancy is maintained. So as of today, about 31 to 32 satellites are there in the GPS network at a point of time, whereas the GLONASS and the Galileo, they use a 3-orbit system. So that is how these systems differ. Whereas the Chinese model is a little more complex. They are using the medium Earth orbits, the geosynchronous orbit, and the inclined geosynchronous orbit and the geostationary orbit. So they have a mix of different type of orbits in case of the Chinese system. Another thing was that for resolving the position, because we have 4 unknowns actually, latitude, longitude, height, and there is a unknown in case of the time also, because we have atomic clocks on the satellite, cesium, rubidium atomic clocks in case of the GPS, whereas on the ground we have quartz clock. So there is a synchronization problem because of the 2 clocks which are having different precision. So there is a 4th component which is unknown, that is the clock bias. So 4 unknowns, X, Y, Z, and clock bias, which is represented by B. So that makes it important that for these 4 unknown parameters, we make 4 equations to resolve these parameters. So 4 signals are minimum required from 4 satellites. So this is the overall scenario for the GNSS systems, which gives the detail of GPS, GLONASS, Galileo, BEDO, and we can discuss this for 1 hour actually, because there are so much of details in this one table. However, we will take up the key points. So basically, the GPS, which is owned by the USA, it's working primarily in the L1 and L2 carrier wave systems under the basic configuration. However, L3, L4, L5, L1C, L2C, various new carrier waves and signals has been added into it. Similarly, for GLONASS, L1, L2 are there and L3 is there. For Galileo also, host of carrier waves are used along with the codes. Similarly, for the BDO system also. Whereas for the GPS, they are providing the standard positioning service for the civilian applications and precise positioning service for the defense applications. Parallel to it, the Russian system provides standard precision service. So the P is standing differently. Here it is positioning, here it is precision. And for the defense purpose, it is high precision service in case of the US, whereas the open service, safety of life, commercial services, then for various regulatory agencies and search and rescue operations. So Galileo has a multimodal services, including the commercial services for the users. Similarly, BDO also have open services and the authorized services for the civilian and the defense services, respectively. So like we talk about first generation, second generation, third generation computers or aircrafts. Similarly, in case of the various satellites, we have the different generation of satellites which are called as Block 1, Block 2, Block 2A, Block 2R, Block 2RM, and Block 2F. So mostly the current dependency of ours is on the Block 2F, which is having the L1, L2 as well as L5 carrier waves, and the recent are the Block 3A, which are being launched. So few of the satellites of Block 3 has been launched. In the recent what has happened, the cyber security has become a very big issue, and there is a more threat on this part. So this Block 3 actually is a overhaul of the entire GPS system, which will take place with the cost of about $6 billion in the times to come, with the entire new ground hardware. So entire hardware has to be replaced on the control stations, and the entire new software. So the software which they are using now in itself is costing about $500 million, which takes care of the cyber security part. And this will provide a strong military code for the US, which will be used for their aircrafts like F-22, Hawkeye, and other aircrafts. S-band telemetry is there in this, and this GPS-3 will deliver 3 times better accuracy and provide us up to 8 times improved anti-jamming capabilities. Because you know, wherever there is a problem going on across the globe, the GPS jammers has been placed by various countries, which in general is illegal. However, the defense agencies are putting it across the borders for their requirements. So this Block 3 satellites take care of them also, partly by having the anti-jamming features also. Another thing is that we are talking about the global navigation satellite system. So we are looking for the interoperability. So some of the signals are launched which are common in various navigation systems. That is the GPS, GLONASS, Galileo, BDO, IIRS, QZSS. So they are lying in around L5 carrier wave. So this signal is now, common among all the systems to have the interoperability for the various systems. Now all these things are happening very transparently, and all the countries, including China, Russia, US, Japan, India, European Union, all the details of the satellites are transparently given on their websites, with interlinkages of their websites also on each other's page. So that is the type of the coordination they are having currently. So the latest scenario is that the Block 2R, 10 satellites are there, Block 2RM, 7 satellites are there, Block 2F, 12 satellites are there, and Block 3 has 2 recently launched satellites with the new signals. The initial life of the satellites used to be about 7.5 years, and with the current life of the 15 years in case of the GPS. Similar developments happened in case of the GLONASS also, where the development of the technology has brought more efficiency to the electronics and less weight to the satellites, and primarily thus affecting the power requirements also and directly affecting the lifetime of the satellite. So from 3.5 years, it has also increased to the 10 years. There the various generation of GLONASS satellites are called GLONASS, GLONASS M, GLONASS K, and GLONASS K2. So GLONASS K2 is the running model of the GLONASS satellite. So because these are also using different type of satellite buses, wherein the equipmentation is being done. In case of GLONASS, the minimum requirement is actually 18 satellites for the minimum operability. However, they also maintain 24 to 27 satellites at any point of time. So with 18, they have the minimum function, full functionality, whereas with the 24, they have a full constellation, we can say, and further they put more number of spares in GLONASS also. So initially the GLONASS was giving the frequency division multiple access signals only, FDMA signals, but post 2006 development where the Russia and US came together, the GLONASS also started giving CDMA signal, and thus made it possible us to realize the concept of GNSS. So I have given most of the screenshots of the web pages, and addresses are also given, at least one to begin with, for all these different systems. So different type of clocks are being used here, which are having a very high accuracy of the order of 1 in 10 to the power 13 to 1 in 10 to the power 15. So different atomic clocks, hydrogen measure clocks, cesium clocks, these are being used. And final timing, which is basically used, is actually an ensembled solution. It is not a single clock which is giving us the value of time. Thereafter, we can see how we can understand any of the satellite systems. For example, here we are taking the case of the GPS, but similarly we can understand for the GLONASS, BDO, any other system. So any of the single GPS system, or on the whole the GLONASS system, can be understood in 3 segments. One is the space segment. So the space segments constitutes the satellites which are orbiting in the space, launched for the purpose of the navigation. Then we fall under the user segment primarily. So we, as a user or the application scientist, we are using the positioning, velocity, and timing parameters of the GPS for any of our applications. It can be civil engineering mapping application, or it can be agriculture, precision agriculture application, or transport related application. So we are using it for that. Then there is a control segment, because we have to launch the satellites, and after the launch also somebody has to take care of the satellites. The maneuvering of the satellites is required. So for that, monitoring and control stations are there in each of the satellite navigation systems. So here right now we are taking the example of the Navistar GPS. So in case of Navistar GPS, the prime space segment contractors have been the Rockwell International initially, and as they follow the tendering systems. So it went to Boeing later on, and then it went to Lockheed Martin, and again then it went to the Boeing. And currently the satellite buses which are being built are, that is the block 3 of the satellites, it is being built by the Lockheed Martin. The GPS is being using the WGS84 datum. The final command is with the US Air Force Space Command at Colorado Springs. It also shows pictorially. So this is the satellite segment, this is the user segment. So user segment actually is in the ocean, on the land, in the air, or in the space also, because the satellites which we are launching, they also have GNSS receivers nowadays. So their position at any point of time in the orbit can also be assessed with the help of the GNSS signals. And then there is a control segment also on the ground. So this depicts the GPS system components. So minimum 4 satellites are there in each of the orbit. These are 6 orbits at a distance of 60 degrees along the equator, at an angle of 55 degrees to the equator. So these are placed so that they are having 12 hourly orbits. Any of the satellite is in view from the ground stations for minimum 4 to 5 hours, and it is in such a way that minimum 2 ground stations can have connectivity with the satellite, and the average elevation is the 20,200 kilometer. The decisions regarding the GPS or the Navstar GPS are taken by the PNT Executive Committee. So now this is the base configuration, or we can call it a zero configuration. So when the GPS was conceptualized, it began with the development of the 5 ground stations at Quezon, Diego Garcia in the Indian Oceans, Ascension Islands, Colorado Springs, and the Hawaiian Islands. And with the help of these 5, the basic GPS system operates globally successfully with full completeness. However, as the time moves and the situation internationally changes, new ground stations have also been developed, and currently there are 16 monitoring sites or stations across the globe with the friendly countries. They have put it, the USA, and they have 12 ground-based antennas also for it. Out of these, 6 are owned by the Air Force and 10 are maintained by the National Geospatial Intelligence Agency. So NGIA is owning the 10 of the satellites, and this is the current scenario. However, we should remember that this is the base configuration. Okay, but because whenever we have to understand the working, we have to start with the basic model. Then it will become easy to understand the advanced model, because advanced model is continually advancing. So somewhere we have to start. So it is better to start with the basic model, which requires minimum 5 ground stations. And advancement is also endless. So it is a perpetual activity. So we cannot start from the most advanced one. So that is how we are explaining here the control segment. Now, in the control segment, there is a master control station at the Colorado Springs and the monitoring stations across the globe. So what are they doing actually? So the monitoring station's role is to basically measure the pseudo-range data, and basically what they do is at the monitoring station, they are like the data collection hubs. They track the various satellites, get the information about the broadcast ephemeris and the satellite clock parameters, and they send all these data sets to the master control station. Now it is the responsibility of the master control station to correct all the errors in these parameters. And after the corrections, all these parameters, basically the broadcast ephemeris data, which is converted into the precise ephemeris data, and it requires about 10 to 14 days of time, which is taken by the master control station. After doing the correction in the ephemeris data and other data sets, they upload these data sets online on their website, which can be accessed and downloaded by us for our processing at no charge. So it is a free of cost service which is available, and these ground stations spread out, they take care of the maintenance also. They can do the uploading or the updation of the softwares for the satellites which are in contact with them at that point of time. Similar ground station network is with the Russia also. So these are the stations which are shown in this diagram. In case of the Russia also, similarly ground stations and master stations are there. So the GLONASS, actually what was happening in case of the GLONASS, initially they started with the by using 24 frequencies, but then they faced the radio frequency interference problems in the GLONASS signals, where they decided that okay, at the antipodal positions we will use the same frequencies. So they started thereafter using 12 frequencies instead of 24 frequencies. So these are the formulas, simple formulas are there, that L1 is 1602 megahertz. So then for the next satellite, the L1 value will be multiplied by n into 0.5625 megahertz. So that is how initially 24 frequencies were used for L1 itself and 24 for L2, but thereafter they reduced it to 12 by having the same frequencies for 2 satellites at the opposite ends of the Earth. So one to one side of the Earth and to the other side of the Earth, because in any case the same receiver will not get access to the 2 signals at the same time. The frequency ratio of F2 by F1. In case of the GLONASS is capped as 7/9. So that was the satellite segment and the ground segment. Now the third segment is the user segment, where we all fall in. So user segment is a very vast segment, and almost in every walk of life we are using GPS or GNSS services, either directly or indirectly, by getting position or velocity for our navigation or timing also. So I'm not reading the list of the users, but there are endless users, and so many applications have been running all across the globe using the GPS, where even very complex applications like the power systems, which take care of the national grids, they also take care of the timing with the help of the GPS systems. Then why we are using GPS actually? Because it is weather independent. From the surveying point of view, it is very helpful because it do not require clear line of sight, and it provides high geodetic accuracy. It can be operated day and night, has very economical advantages. It's working in the common coordinate system. So it is the first system which provides us a seamless connectivity in the coordinate system across the globe, which can be used for all kinds of activities such as construction of roads, railways across the various countries. So there are various plans you might be already aware, from Singapore to UK, the China to France, Germany, those all connectivity of the railways and the roads, they are becoming possible in today's environment, and it provides a lot of convenience to the engineers which are working with the WGS 84 system across the borders, because they can talk in the common terms then. How fundamentally the GPS is working, it can be explained in 5 easy steps. By using diagram, we will explain it. So at time T1, the signals are starting from the satellite and they are reaching the receiver at time T2. So the travel time is T2 minus T1. So this delta T is multiplied by the velocity of light, and this velocity of light gives the pseudo range. So now in surveying, we are calling the distance as the range. Now pseudo means false. Now we call it pseudo range instead of range because there are certain errors which need correction. So using this pseudo range, we can place the receiver somewhere on this sphere around the satellite. Now why around the satellite? Let us recall the Frank McLure, his idea of inversion of the problem, from where the development of cyclone transit and the satellite-based navigation started. So the coordinate of the satellite is known, and then the pseudo range is known. So we can make this sphere around it. However, there is a large uncertainty right now with one observation only. So the receiver is somewhere on this sphere. So instead of that, if we create two spheres with the help of the two pseudo ranges for the two satellites, they can intercept and they can reduce the uncertainty from the whole sphere to the circle. So now the somewhere on this circle the receiver is there. Same when we do intercept the three spheres, then it results into the two possible locations of the receiver. So out of this, one is the real solution and one is the vague solution. So that means with the help of the three satellites and the signals, we are able to get the position of the user by the intersection of the various spheres. Okay. So now here we have considered a very ideal position that there is no problem in the timing. But now because we know that there is a problem in the timing also, and timing is very important in this whole computation, because 1/10 of an error can lead us away from the point of interest by 30,000 kilometers. 1 microsecond error can take us away by 300 meters. So these errors are not tolerable in many of our applications. In ocean applications, possibly 300 meter can be absorbed at some locations. However, for urban applications, water source applications, we need centimeter to millimeter level accuracy. So we need clocks which can provide us an accuracy of the order of 1 in 10 to the power 13 or so that we can get centimeter to millimeter level of accuracies. So we have finally 4 unknowns: latitude, longitude, and height, and the clock bias. So for these 4 unknowns, we need 4 independent equations which can be resolved to solve the coordinates and the clock bias. So for that we prepare such equations. So pseudo range, that is the P1, and Z, and the clock bias, that is the B. So these 4 unknowns remain for the user location. So using these 4 equations, it can be resolved. This is require a non-linear solution. So we have to linearize the equations. However, this can be done easily with the help of the today's computers and computational environments. And this is being done at the GPS receiver end, wherein it calls for the first fix. You might have heard of the voice fix is achieved or fix is lost when you are using the GPS. So when it says fix is achieved, so that means the solution of it has been achieved. We have the X, Y, Z. When fix is lost, then that means the GPS receiver is not able to resolve the equations, and at that point of time the values became less reliable. Now for our global civilian timing, we are using the UTC or the Zulu calendar, Universal Coordinated Time, or the International Atomic Time. However, for the GPS, the timing is understood in a little different way. So the GPS timing starts from the first Sunday in 1980 on 6th January, night 12 o'clock. So from there, the counting of the GPS time starts. The GPS time starts with 0 at beginning of each week also. So the computation of GPS is little different from our civilian time. At the time of the beginning, that is the 1980, for the GPS time, there was a 13 leap second difference between the International Atomic Time and the GPS time. However, we need not to worry about it. It is taken care by the satellite navigation agencies. Just a minute. Now coming to the GPS signal structure, again I will talk about the basic structure first. So there are 2 carrier waves, that is the L1 and L2, which are powerful waves, and they have the capability to travel from the satellite to the receivers, and they are modulated by the codes CA code and P codes, which are relatively weaker in terms of energy, and that's why they are modulated on the L1 and L2. CA code is only available on the L1 carrier wave, whereas the precise code, which is for the defense purpose, is available on the L1 as well as L2. And the P code is actually encrypted using the W key, and that is why it is known as the anti-spoofing procedure. And the code, instead of being called as P code, it is called Y code after the encryption. Now the P code frequency is considered as the fundamental frequency, that is the 10.23 megahertz. When we multiply it by 154, we get the frequency of L1. By 120, we get the frequency of L2, and when we divide it by 10, we get the frequency of CA code. The CA code initially, because as we have understood that the satellite systems, navigation systems, has actually originally being developed for defense purpose only. So how CA code has been there for civilian purpose? So basically, CA code was not meant for civilian purpose initially. It was meant to catch hold of the P code. So they have a mechanism that once they catch hold of the CA code or retrieve it, and with the help of the CA code, actually they catch hold of the P code. That is how the defense authorized receivers works. However, when the decision was taken care that the GPS signals will be available for the civilian purposes, then they left this CA code for the applications which are required for the civilians. So this is the basic configuration or the zero configuration, which has two carrier waves and two type of codes. One is CA code, another is the encrypted code. And these L1 has bandwidths also of 24 megahertz, L2 has 22 megahertz, L5, which is the new one, that has 28 megahertz. The wavelength of L1 frequency is 19 centimeter. For L2, it is 23 centimeter. In case of GLONASS, the fundamental frequency used is 5 megahertz. Besides this basic configuration of carrier waves and the signals, the GPS satellites also give a 50 bit per second satellite message also, which includes the almanac and the ephemeris set. Almanac is the chart of the entire set of the artificial GPS satellites, whereas the ephemeris provides the instantaneous coordinates of the GPS satellites. So now L1 and L2 are there. Besides that, L3 and L4 are also there, which are used for the nuclear detonation identification across the globe. This is available to the US agencies only. So this is not for us actually. Then L5 has been started from the Block 2X series. So L5 has 1176.45 megahertz frequency, and it provides us indoor applications and anti-jamming features, and it has a period of 1 millisecond only, and it is being used for the safety of life applications. So this is the L5 which has been added later. Then L1C and L2C are also added. Now this L2C number of satellites with the L2C signal are sufficient. However, still it is being in the pre-operational testing phase only, whereas L1C are starting with the third series. So only two satellites are there with the L1C signal. So in the times to come, we are going to use these also, and these will be used for the civilian applications also, providing us higher accuracy with the correction of the ionospheric errors also. So that possibility is there in the times to come. Then in the new one, they have added the military code also recently. Now, how they are resolving the clock bias? So what is happening that a signal is sent by the satellite and the receiver also generates it, and they are the same signal and they have to match together. And this matching is carried out by keeping one as the constant and another as the moving. So the amount of shift which is required to just overlap them, that amount of shift gives the computation error for the synchronization, and thereby we are able to compute the clock bias, and we can compute based on that the delta t or the error in the distance because of the clock bias. So this is one of the distance. This is not the distance between the satellite and the receiver, but this is the distance here representing the error which is there in the pseudo range. Okay. Again, here we have to understand there are two types of errors we are talking about. One is the error in the pseudo range. That means the error in the computation of the distance between the satellite and the receiver. However, when we talk about the final errors in the GPS, then we are talking about the positional errors in the observed point. So these are the two different types of errors. So this can be done with the help of the code observations. The code observations can be used to provide the code-based solutions, which were the initial solutions. They can provide us with the accuracy of 10 to 20 or 10 to 30 meters of errors in positioning. Whereas if we do the same exercise with the help of the phase, then it is possible to get an accuracy of the order of centimeter to millimeter based upon the type of survey scheme which we have used and the type of the processing. So these two methods are there, code-based solutions are there, and the phase-based solutions are there to compute various type of errors and final positioning out of it. Now, coming to the satellite geometry, the basic question is, suppose if we are getting 4 signals from 4 satellites, and or let us say 10 satellites. So if you are able to see me, I am holding my hands like this. So you assume that these fingertips are the satellites, and the bottom of my palm is the receiver location. So if there are 10 satellites giving the signal, so the fundamental thumb rule is that higher the volume, more is the accuracy, lower the volume, low is the accuracy. So in case of GPS, like we use root mean square error in mathematics statistics, in case of GPS, we have a parameter called the dilution of precision. Instead of RMSE, we can say we have a similar analogous parameter called dilution of precision, which reflects the quality of the signals which we are getting and thereby affecting the final accuracy. So this dilution of precision can be of 4 types. If we are computing it for the latitude, longitude, height and time, it is called geometrical dilution of precision. If we are computing it for latitude, longitude and height, it is called positional DOP. If we are doing it for latitude, longitude, it is HDOP, horizontal DOP. If it is for height, it is for VDOP. So various applications may require different values which need to be computed. Accordingly, the parameters can be chosen. And this is a unitless number, so it is very useful for
model choice. So that is very important. So
I did not get it. Kindly repeat. Any question was there? Please repeat.
No, sir. You continue, sir.
Okay, fine. Sorry. So these 4 type of dilution of precision parameters we are using, and any layman who is not having the technical knowledge of GPS or engineering, they can also use the indicators like the pilot or other people. They can use it by just having a look at the DOP value. If it is 1 to 3, it is considered good. If it is between 4 to 5, it is between 1 to 3, it is very good. 4 to 5, it is good, and up to 6, we use these values. Beyond 6, we say that these values become little unreliable. So this is the position which we are depicting here for the good GDOP condition, whereas this is for poor. So you can see here, when we have a wider spread of the satellites above the receiver location, we are getting a better geometrical situation. Why? We will see that. Whereas if they are skewed to one side, then we are getting the less accuracy. So geometrically, we will understand this by this slide. This, please see that this is not the position. This circle is not representing the Earth here, but however, this circle is representing the user location at the center of it. And these 4 satellites are above the user location. So this is an ideal satellite situation, because when we intersect the various spheres to receive the final position, the uncertainty will be less. Whereas when we have a skewed setup of satellites, then the uncertainty will be large. Okay, so I hope you can understand that. So that is why the position of the satellites at a point of time becomes very important. So if you are moving in a area which is a hilly area, or if you are moving in a urban canyon where you have a high-rise buildings, to one side you may receive fewer signals from another side. So at those times the overall accuracy of the resolved coordinates may be little poorer compared to the accuracy what we are getting in the open area. Now coming to the Indian Regional Navigation Satellite System, see, we have launched, you are aware that we have completed our regional satellite-based navigation system in 2016, and we are maintaining 7 satellites in it, and it is providing us an PNT services across the Indian region as well as 1500 kilometers beyond the Indian boundaries. So this system also has a standard positioning service for the civilian applications, and for the authorized users, it has restricted service also. It is using L5 signal and the S-band signal, because the International Telecommunication Union has provided us L5 and S-band to use. So this is the system which is first in its category, because no other navigation system operates in the S-band region for the primary signals. So we are first in that case. So L5 and S we are using, and these are the series of satellites, IIRS 1A, 1B, 1C, 1D, 1E, F, G, H has failed, and 1 I. So these 8 satellites are orbiting in their orbits. So out of which 7 satellites are fully operational as of now, leaving the IRSS 1A. 1A has an atomic clock issue. So rest of the 7 are fully functional and providing us continuous services. The signal in space ICDs. ICDs are interface control documents which gives the basic physics behind the signals. It is released in July 2019. Before that, the older version was released in somewhere in 2017, and it gives all the details for the application people who want to make some applications using these signals. So INCOIS has already operationalized it for the purpose of the fishermen. Various type of signals are being sent to them in their GPS receivers if they are using in their boats for their safety. So the signals 0111 for the high waves, 4 times 1 for the cyclone warning, tsunami 0011, and no warning. Normal condition is by 1100. So already these applications are there in operational mode for the fishermen working across the boundaries for the purpose of the shipping. Another thing is they get a SOS message if they are in the extreme areas of the Indian borders. So they do not, so that they do not cross the Indian borders. Otherwise, we know that various problems we are getting. They are being captivated by the other countries if they get into their water region. So this is a very important application wherein we give the signals to the fishermen that you remain in our own borders, and including these 4 signal positions status also. Now the last big development is that the International Maritime Organization has also recognized IRSS, because somewhere a few months back the international body 3GPP has certified the IRSS signal also, because we have to produce the signals in a format so that they can be put into the various formats which are required for the processing, like the RINEX format, SINEX format. So all those formats has been defined for IRSS parameters, and that was certified by 3GPP earlier. Whereas now for the purpose of the use in the Indian Ocean, from 5 degrees south to 50 degrees north latitude and 55 degrees east to 110 degree east longitude, IRSS is fully operational. It has been operational for quite some time. It is just that now it has been certified by the IMO. So very safely our people can use it without any doubt on it. This service is fully operational and they should use it. And with this, India has become the 4th country after US, Russia and China, which is providing the services to the IMO. Coming to the GPS surveying techniques, you must be aware that when we are using the remote sensing data, we have to do the georeferencing for it. And for that, we conduct surveys by putting one receiver at the known location and another receiver we are putting at the unknown location. That is, we are referring it to as the differential GNSS survey, wherein we find the correction parameters at the known location, because that location is known. Let me show you that slide first. So we have known parameters X, Y, Z at the base station. And from the broadcast ephemeris, we get the coordinates as X dash, Y dash, Z dash. So delta X, delta Y, delta Z, that is the error at the base station, can be computed. Let us see, this is the base station and the user is here on the ship, and which can be a mobile user also, that is which is moving. So the corrections delta X, delta Y and delta Z are computed at the base station, and they are transmitted to the user either through an antenna or a modem, and thereby correcting the user position. So that is called the differential GPS or the differential GNSS method. So this method we are using for finding the unknown points on the ground for georeferencing of our remote sensing data sets or any other application. Okay, for our purpose, we are taking an example of remote sensing data sets. So if the longer baselines are there, that is the distance between the base station and the unknown location. If it is of the order of 20 kilometers or more, then we call it a static method. Whereas if the distance between the base station and the rover station is less, of the order of 5 km, 2 km, or 10 km or so, we call it a rapid static or fast static survey. Why we do so? Because when we are processing the data, minimum 4 satellites should be same between the base station and the rover station. It is possible that at the base station you are receiving signals from, let us say, 15 satellites. Today, because we are talking about GNSS, such large number of satellites are very easily available. At the rover stations, you are receiving signal, let us say, from 12 satellites. So out of these 12 and 15 satellites, minimum 4 satellites should be common. And that basically define the time of observation of the or the time of occupation at the rover station. Rover station is the GPS station which we plant or which we install at the location for which we want to compute the coordinates. So they are the rover stations. Another thing is for utility mapping, like let us say mapping of all the electric poles, manholes, hoardings in a campus or in a city. We just want to have a value and we do not need very high accuracy there. Let us say the location of the tree. Now tree canopy itself is 5 to 10 meter wide. So we need not to worry about the accuracy in meters, centimeters or millimeters there. So what we can do is we can just take our observation there and move to the next point of interest. So such methods we call as stop and go. Then there are some applications where we want to continuously track the trajectory, like the cabs, like the aircraft from takeoff to the landing. So we want to map the complete trajectory when we are firing the missiles. So the missile track when we are testing the missiles. So that trajectory we want. So there we can install the GPS. So that means we are using the kinematic mode of utilization of GPS signals. That is the differential GPS. Because of the shortage of time, I have explained it very quickly. I will repeat it once because of its importance. Basically, what is happening, we are using a known location which we refer as base station, and its XYZ coordinates are known from the previous survey, or we can compute it ourselves by doing some 72-hour survey method. Some different methods are there. And when we are doing the survey for some other applications, using the broadcast FMS data, we are getting the coordinate x dash, y dash, z dash. So using these, we can compute the error at the base station. And that can be used as the correction parameters for the user. Now this can be very comfortably done for some of the baselines. So we can use a Trimble Business Center or Ski Pro or the Leica Geo Office, such softwares we can use. However, if you want to use it for distances like Jammu to Dehradun, to Delhi, to Hyderabad, to Bangalore, to Chennai, if we have very large baselines, then we will prefer some scientific softwares like Bernice or Gamut, wherein we can put weather parameters also, because for small baselines, we can use the same correction parameters for base and rover stations. But for longer baselines, 500 kilometer, 1000 kilometer baselines, what will happen that the weather parameters will be different, atmospheric conditions will be different. So the ionospheric corrections, tropospheric corrections, they all need to be computed separately for the base station and the rover station. So there, these softwares like TBC and the Leica Geo Office, which have standard models like Sestimonian and the Hopfield models for the corrections, they may not be sufficient. So there we need to use the Bernice or the Gamut software. Now this can be done using a post-processing method. We can do the survey and we can come back to the office and we can download the data and we can process it. Or in the real time we want to do it, then we have to use a modem to transmit the errors as the correction parameters. So here, this slide shows, suppose this is this yellow line, this polygon is your work area. So we can define their control points like this and base at somewhere in the middle with possibility of using it as a control point also, or it may not be used. Both the possibilities are there, and that will provide good georeferencing for the two-dimensional applications for the satellite data sets or photogrammetric data sets. It can provide the possibility of doing the absolute orientation. So in the photogrammetry, we are doing in interior orientation, then relative orientation, and the absolute orientation. So these coordinates can be utilized for the purpose of the absolute orientation, providing the leveling and scaling to the 3D model. So that is how this can be used in the 3-dimension as well as the 2-dimension. So this is the radial solution which we are showing to depict in case we have 2 receivers only. So one receiver we can use at the base and another receiver we can use at the rover station. That is the location of the GCPs. However, the ideal solution is if we have a 3 receivers. So base we will have 1 receiver, at the rover location we have 2nd receiver, and the rover location 2nd we have the 3rd receiver. So we will have a triangular solution. So we can apply better least square methods and we can compute higher accuracy. See, all the accuracies which vendors are providing in their brochures, they are the best method, and this is the best method where we have triangular solutions. We have to process the base station with the IGS stations. Then only we can think of achieving the centimeter to millimeter level of accuracies. So what we are doing here, we are establishing base station R1 and R2, 3 stations we are establishing, doing the common observations, so that we should have sufficient observations so that we have 4 number of receivers, 4 number of signals from satellites common between R1 and base and R2 and R1 and R2. Once that happens, then R1 is shifted to R13 location. Next triangle will become base R2 and R1 by 3. Once this observation is complete for this triangle, then R2 will be shifted to R2/4. So in this triangular fashion, the entire survey can be completed when we have 3 or more number of GPS receivers. So ideally, this is the most ideal solution which we do for the all precision applications for our national mapping surveys or national networks. Coming to the receivers, so we have receivers which work only on L1 frequency. So the older set of receivers are giving us an accuracy of the order of 1 centimeter plus 2 ppm, whereas the latest receivers are providing us an accuracy of the 5 millimeter to 1 ppm. See, there is a report by for the Navstar GPS. This is the 5th report on the standard positioning service, which is recently released by the US agency. It says that the latest receivers, properly built up receivers, can provide accuracy of the order of 3 meters in horizontal and 5 meters in terms of the vertical. Initially, these values we were considering as 10 to 20 to 10 to 30 meter of accuracy. So some changes has happened recently that if we take the latest receivers, we can have better accuracies. So similarly, in the dual frequency where we have L1 and L2 signals, or multi-frequency where we have L2, L1, L5, not only from the GPS but from GLONASS, Galileo, other systems. So we can call them as multi-frequency receivers. They are capable of providing us currently 3 millimeter plus 0.4 ppm accuracy in horizontal, and in vertical 3.5 mm plus 0.4 ppm. Earlier this was 5 millimeter plus 1 ppm. So these are the recent developments wherein we are getting very high accuracies either from the single frequency receiver or from the dual or multi frequency receivers. Okay, but then why we should use dual or multi frequency receivers when we are able to get 5 millimeter accuracy from the single frequency receiver itself? See, basically what happens that with the single frequency receiver, there is a limitation of the baselines. So single frequency receivers are suggested for small baselines of the order of 15 to 20 kilometers. So if you have a small study area, then you can use single frequency receiver. However, for the larger study areas or the nationwide studies, we cannot use single frequency receiver. We have to depend upon the dual and multi frequency receiver, and we should process the data in those cases with the help of the Bernice or Gamut software. Gamut is free of cost, which can be downloaded from the MIT website by doing a registration, and Bernice we have to procure from the University of Bern and the Switzerland. So they are providing the Bernice software, and the Gamut we can get the free download. However, Gamut is in the Linux, so that is the only issue with the Gamut. So now there is another classification of the receiver based on the type of working. So geodetic class of receivers are providing sub-centimeter level of accuracies or the millimeter level of accuracies also. Mapping grade receivers are considered which provide better than 3 meter accuracy, or navigation grade receivers are called which can provide 10 meter of accuracy. But however, these boundaries are very hazy. Actually, there is no such practical classification like we have in the case of mapping large scale maps, medium scale maps, small scale maps. So these are relatively used. However, for the purpose of geodetic accuracy, we are using the best methods with the best processing methods, best surveying methods, stringent measures, so that we can actually use it for sub centimeter or millimeter level of accuracies for the applications like tectonic movement and so on. So this is just to provide a GIS view that from the GPS we can have a point observation, we can have a line observation, or we can have a area observation using the points which we are getting from the GPS. So that is how we can use it in the GPS. In today's environment, all the technologies have been integrated. GPS, SIM card for the mobile camera, GIS software, total station and GPS are combined in the smart station by Leica. So same setup as the total station or the GPS, because the field engineers, they are having the old topo sheets which are referring to the mean sea level datum and the average ellipsoid in one hand, and on the other hand they have the GPS. So there is a difference in that. So that helps us to make them difficult tasks work out, such as the tunneling operations, because the tunnel is being using the TBM machines, they are being bored from the two ends. So such engineers, they require very accurate calculations of the contours and elevation points, and they need the transformation parameters by understanding the geoid undulation also. So the smart station by Leica, which has total station and GPS together, such kind of systems are also very useful. So that is how we complete. Now one case study I will take here for photogrammetry. So this is the generic chart. We have area where we can have aerial data set or UAV or satellite based data sets, which can also be either in the magazine form, which can be digitized using the scanning, or they can be in the digital form itself as a digital photograph from the camera or from the images. So these can be used. If it is magazine, then we have to take the photo processing and we have to take a positive and we have to take it to the field for the ground control survey. If it is digital data, directly we can conduct the ground control survey for the GPS observation. And these GPS points we can use at the stage of the absolute orientation, either with the aerial data for aero triangulation or with the satellite data for the satellite triangulation. Once we do the triangulation and the bundle block adjustment, we can generate the digital elevation model. So the triangulation we have to keep within 1 pixel. See, when we mark a GCP, the accuracy of the GCP is considered to be of the order of 0.5 pixel. We cannot have exact pointing because it's a pixel. So in the pixel we are marking. So suppose, for example, we have a cartosat 1 data, 2.5 meter data. So once you mark the GCP into it, it is of the order of 0.5 pixel. What is 0.5 pixel? 0.5 of 2.5 meter. That is 1.25 meter is the pointing accuracy at the stage of the GCP marking. But when we are doing the triangulation, we have to bring the accuracy for the bundle block adjustment within a pixel. So that means that is the accuracy for the which we are aiming either in the satellite triangulation or aerial triangulation. In UAV, we are getting the pixels now of the order of 5 millimeter also. Earlier, we are getting of the order of 2 centimeter to 5 centimeter. Now we are getting of the order of 0.5 centimeter, that is 5 millimeter. That means there is a possibility to mark a GCP with an accuracy of 2.5 millimeter also. But to achieve a 2.5 millimeter accuracy in a GCP, we have to conduct the GCP survey in the differential mode with the best of the best method. So remember, there are methods like precise positioning method, which has come now using the paid services either through the internet or through the satellite directly through the license. But they are giving an accuracy of the order of better than meter, like 80 centimeter or so. They cannot be used for the purposes of the UAV. So once we do the bundle block adjustment, we can do the DEM generation or we can do the stereo data capture in the photogrammetric environment. From the DEM generation, we can do the ortho images generation and we can do the contouring and we can overlay the contours on the generated maps, either 2D or the 3D maps, generating finally the digital or the hard copy maps. The beauty is that now these outputs, digital outputs, are in the formats which can be taken into the engineering softwares also directly. So because in 3D environment, when you digitize the road, every vertex has X, Y, Z. So if you have a water pipeline project, so using the stereo data capture, the photogrammetric output can be directly taken into the AutoCAD map, AutoCAD water or AutoCAD sewerage softwares, wherein the directly engineered applications can be using the remote sensing outputs. So remote sensing outputs or the photogrammetric outputs can be made the input to the engineering application softwares or cut and fill calculations for the roads or railways or in the construction of dams. So we are doing the surveys in the so this is showing a base station which we have put on the roof of one of the guest houses. This is the GCP location at the end of a bridge. All the GCP should be clearly visible when in both the left and right images of the stereo data or in the two-dimensional image if we are using the mono images only. So we can generate the DEMs, we can generate the grid-based DEMs or the tin-based DEMs. We can do the mapping, we can prepare the maps, we can overlay the contours on the maps, and we can use it for various purposes like applications, mapping, or for other engineering applications. So this is these are the outputs from various projects. So basically, this is the stereo vision system for photogrammetry, wherein we are using the GCP points. These GCP points can be marked either in 3D environment or in the classical mode of 2D environment, as you might have seen in the socket set software or the Leica photogrammetric software. So various systems has been there, analog systems, analytical systems, and the today's digital systems which are used. This is one sample image which come with the analog systems. This is a Switzerland area where GCPs are marked. So this is a part of the analog system. So this is how we make the stereos. Just already you must be aware in the photogrammetric part how we are using the parallax. We are getting the height information in photogrammetry. If we have a large set of photographs, we are making the block. So and we are finding the control points in a very critical way, that the control points should be, because it is a huge investment to collect the control points either on aerial photographs or the satellite images. We do the basic survey and provide the photo control on these images as per the application, whether it is a 2D or it is a 3D, because the stringent requirements will change. So minimum requirement to compute the scale is the 2 control points that we know. For the purpose of leveling, 3 vertical control points are required. So if we have 3 full control points, we can find the parameters for leveling and scaling of the stereo data sets. However, to have least square adjustment for the purpose of proper error distribution in the model, we should always have some redundant observations. So when we do specific studies, let us say for one cartosat scene, so although the solution can be obtained by 3 full control points, we are normally using 15 to 20 control points. So some of them can be used as for the purpose of the bundle block adjustment, and some of them can be used for the purpose of the checkpoints. So some points we can use for the purpose of the solution of the block, and some other points for the measurement of the accuracy. This is another application. Like in the previous slide, those screenshots were from Jaipur, Dehradun region. Now this we have conducted earlier this survey in the Maldives, where the features on the grounds are missing. So you can see here what we have done. In that case, we have put the artificial markers on the ground at the time of the aerial flight. So the document is available here. So these artificial markers are now available in the aerial photographs, and we can do the GPS survey. So in such tricky areas, because similar situation you may find in the deserts of Rajasthan or dense forest areas or the areas which are having uniform features all across the scene. So there it is becoming very difficult to find any control point. So at such locations we can use artificial markers. Now currently we have a lot of open source DEMs which you might be using in your various projects. So currently the best of them is the LS Pulsar DEM, which is at 12.5 meter, and TandemX also, which is provided free of cost at 9 meter. Although the paid version is at 5 meter for TandemX, they are giving us an claimed accuracy of the order of 1 meter in height in tandem-X. So theoretically, as per the claim, tandem-X is the best DEM which is providing us the best accuracy right now. However, we can do DEM fusion also to generate still better DEMs, like the one attempted by University of Tokyo is the Merit DEM, and one by the NASA, that is the Earth can be 90 meter. So these two fused or assimilated DEM are also available, which are generated by using the SRTM DEM and the ESTA DEM. Okay, but you should use it with caution, because as we have tested, Cartosat 1 DEM version 3 release 1 dataset itself is providing better accuracies than the fused DEMs of Merit and RTNV in the plain regions of India. So for the Indian region, Cartosat 1 DM can be downloaded from the Bhuvan website of NRSC. Similar DMs for European Union and other regions of the world are also applicable. These are the website locations from where these kind of datasets can be downloaded. And these DMs are not only used by one technique, but various techniques like photogrammetry, SAR interferometry, altimetry, radargrammetry. Many methods have been used to generate them and then improvise them. This shows the international GNSS station locations in India now. Currently, one is at Lucknow, another at ISC Bangalore, and GRI Hyderabad. So these stations are also increasing in number in India. Earlier, we used to have only one at ISC Bangalore, then and GRI Hyderabad. Now we have one more. So this is the table which shows various kind of applications, and all of us can place ourselves in somewhere in this. So if it is a GIS database problem, utility mapping problem, then we need accuracy of the order of 20 centimeter for our projects. For GIS data collection, site-specific farming, 1 to 5 meter accuracy, reconnaissance survey, normal receiver, handled receivers can be used for reconnaissance surveys. If we are working for tectonic studies, geodetic infrastructure, fault monitoring, then we need centimeter to millimeter level of accuracies. So accordingly, we have to choose the GPS surveying method and the GPS processing method. So both the things are very important for tectonic measurements. So if you want to study it at time T for some incident, normally we are using T plus minus 5 days observations for that. If we have longer observations for 365 days, of course, those also we are using, but minimum campaign mode surveys we are using for 3 days to 5 days. So that kind of processing requirements are there. So currently the GPS signals are available up to 5th Lagrangian point, which is the point of stability between the Earth and the Moon. So up to that, GPS satellite signals are available, and that is why the applications of GPS are now not only on the ground, in the ocean or in the air, whereas the other satellites are also carrying the GPS receivers. And there is a plan in future to put some kind of beacon on the Moon also to provide a seamless positioning from Earth to Moon. However, it is a little far to see that, but there is a plan, definite plan to do that, and it is going to happen in the future. These are some of the basic references for the GPS GLONASS, Galileo, for the ICD documents, interface control documents. Many other references were there on the respective slides also. So I would like to thank you here for listening to the lecture, and possibly we can have some queries also now.
Thank you so much, sir, for such an informative address on the navigation satellite system and its application part. And we will go ahead and take some time for questions now. So anyone has any question, you can directly contact with the sir.
Hello. Yeah, sir, you mentioned about the utilities mapping and no, the 3D mapping of it, and they can be directly transferred to the network softwares like AutoCAD and all. So, I mean, I just want to know more about it. How, I mean, we can just, I mean, handheld GPS जो है tool उसी से हो सकता है? How is it possible?
Basically, क्या होता है कि whatever application we have, basically application is at the forefront. So application will define